All right, so now we're going to make the second row diatomics. So, whether they're 1s or 2s states, they mix and combine the same way that we just talked about it for hydrogen and helium. But that only gets you so far. And then at some point, if you get to the second row, you need to combine p states. And so how do we do that? So what I've got here are two p states, two p wave functions. So these are the figure 8 shapes. The convention that we use is that if there's the bond axis, so the bond would be kind of joining these two, the little black dots here, the nuclei, be joining those. And by definition, we always tend to call the bond axis Z. So this would be PZ and PZ. And note how they're oriented such that the gray part, so like this would be the part of the wave function that has a positive sign. This would be part of the wave function that has a negative sign. They're aligned the same way, that the negative sign is always on the right, and the positive sign is going to be on the left. So let's combine them. The first combination is actually, let's add them first. So I'm going to draw off to the side here. So how do you actually combine these? Well, so I'm going to have two. I'm going to draw them so that they're already overlapped. So it'll look like this. The nuclei are right here. And the difference is that so this is the blue part, and the blue part is here. So what we have here is a region where a blue part overlaps the uncolored part. And that means that they cancel each other out, and that there is a node right there. So if I were to freehand this, which I'm about to do, now something that sort of looked like this. So we have one clear part. This is going to be a blue part, clear part, blue part. Put in our nuclei right here. And so more importantly, this particular combination produced a node in the middle. And if you're doing better pictures, it sort of looks like this. Again, so you will note that the sign alternates. So it is, no color, blue, node, no color, blue. So this is an antibonding combination. So even in this case, the combination where you added them together actually gave you the antibonding combination. So don't necessarily associate addition with a bonding combination. The other one is, let's get the color back here, would be the subtractive combination of the two. So it's going to look like this. And remember that subtraction is merely addition of the opposite. So I'm going to start with my original one. Nucleus and the blue part's going to be here. Now its neighbor, I'll draw the overlap here. Nucleus and shade in blue. Now here, what we have is the region here where they overlap, the same color, the same sign is overlapping, so they add together. So the end result is, I'm going to start with my nuclei this time. A little bit out here, huge addition in the middle, and a little bit out here too. And So this is going to be the one sign, the clear sign. We got the blue sign and in there. So this, if you do it a little bit more pretty-like, looks like this. This is a bonding combination. Now these are still going to be sigma type orbitals. So let's talk about what this is going to look like when you look down the bond axis. So in both cases, we've got our nuclei here. And what you're going to see is let's see, something like this, where you've got the uncolored part and then the blue part. But still, this is reminiscent of an s orbital. Doesn't matter which way you're looking, you see the same thing. So this combination also gets a sigma designation. And here you can kind of, if you've caught on to here, that this is a little tag that tells you the nature of the atomic wave functions that you use to construct this molecular wave function. In this case, it's a 2pz. And these are also sigma types, so this is a sigma star 2pz. So we mixed two orbitals together, we got two more out, so we have two new molecular states. Now, that's not the only possible combination. We could also combine PYs and a PY or PZ with the PZ. And the result here, so the convention here is that we've got, in this case, the colored in phase both up and the uncolored phase both down. And this result, so if you add them together, these overlap and kind of fuse together. These parts overlap and fuse together, and you get this picture right here. Now, what does that molecular orbital look like from the side? It looks, well, it looks exactly like this. So you've got the atoms. You've got one lobe of electron density on top that is the colored kind, and the other one is not. And there is a node that crosses the plane of the bond. So that's why these are called pi-type molecular orbitals, because this has the profile of a p orbital. And they're labeled 2p because they are created from atomic 2p functions. The subtractive combination, this is a bonding one because you've got lots of electron density in the middle there. And so this is the additive combination. The subtractive combination, the overlap in the middle is, they're both of different signs. So there's actually a node right in the middle. That one, if you're not seeing that, I'll draw it for you real quick. So the overlap looks like here. You've got the node where they overlap, and that's why this large gap there is greatly exaggerated, but it makes the point. All right, and I will say that, so this is 2py minus 2py. That's anti-bonding. The 2px orbitals can be combined in the same way, except that they are just, if these are in the plane of your screen, the orbitals from them, everything here would be coming in and out of the screen, but it would have exactly the same shape. You would get one bonding combination and one anti-bonding combination out of that. So we actually now have a total of 6 ways to combine things, or actually 8 types of electrons to combine. We have our 2s combinations, and then the 3, we have a 2px, 2py, 2pz combinations. So let's build a big molecular energy level diagram for that. It looks something like this. Now, this can be a little tricky, but the 2s and the 2p's can also combine as well. But we're not going to try to actually do the drawings for that. So here is the result. This is one way to put these together. And so we note that the 2s electrons and the 2p electrons start with different energies. Now this is assuming that we're talking about, and this is the electrons or the states from atom 1, and the states from atom 2. Now in this case, this is going to be a homonuclear diatomic, so the relative energies here, like the 2p electrons and these 2p electrons, these 2p states, are exactly the same energy because they are the same element. Now the thought is that the overlap between a 2s and another 2s orbital tends to be a bit more than the overlap between a 2p and an adjacent 2p. So these sort of have they start low, they go even lower, and don't go that, and go a little bit higher. But that these molecular orbitals are still lower, even this anti-bonding state is lower in energy than this bonding state. We can label these now, and I'll do that right now. So we've got a sigma 2s, so this is a sigma MO created from 2s orbitals. This is a anti-bonding molecular orbital created from 2s atomic orbitals, or atomic states, and it's anti-bonding. The next one up here is the bonding combination of the 2p states, that is of sigma symmetry. And now we've got a group of 2 of these pi states. So these are the pi 2p's, and the idea is that one of these is the one that's from the 2px combination, and the other one is from the 2py combination. Just like the atomic px and py's, they're exactly the same shape, they are exactly the same energy, they are just oriented, in this case, 90 degrees from each other. Now these are bonding combinations, so these 3 are lower in energy than the original 2p energies. And next we have the anti-bonding combination of the p orbitals with pi symmetry. So this would be the anti-bonding px and the anti-bonding py combination. And then way up here we have the anti-bonding combination of the 2pz's, the one that has sigma symmetry. So this is a ordering you should become familiar with, and it's the same for any, rephrase that, many second row diatomics have this energy ordering. Now you'll note that I don't have anything with the 1s, and more on that in a bit. But what I want to do is actually show you that and give you some better ideas of what these orbitals or these states actually look like. So here we go. So this is the sigma 2s state, and we note that there's no sign change, it's all one sign, no node. This one is sort of like 2 circles smushed together and cut down the middle. So here's the node, here you have a change in sign. This is the bonding combination this is like the pz plus pz combination. And these are the 2, px and py combinations. Again, one's in the plane of the screen, one's coming in and out of the plane of the screen. This is the bonding combination. This is their anti-bonding combination. This is actually a fairly accurate depiction of these. So these are the 2 anti-bonding combinations, again, just oriented 90 degrees away from each other. And last but not least, this is the anti-bonding combination from the 2 px's. So you've got, and again, so you've got a node perpendicular to the bond. And I should note that it is nodes perpendicular to the bond axis that cause problems, that tell you it's anti-bonding. So this node right here is not a problem. This one is. So nodes along the bond axis, not a problem. Perpendicular to it, problem. And this energy level diagram works for, well, some homonuclear diatomics. So now let's talk about that. So the actual energy level diagram depends on what element it is. And you will note, so the one on the left here is appropriate for dilithium, diberyllium, diboron, dicarbon, and dinitrogen. The one on the right is appropriate for dioxygen, difluorine, and dineon. And you will note that this is the one that I just showed you before. This is the one that intuitively sort of makes sense because this 2s overlap is considered to be much, much better than the 2p overlap, which is why these are way down here. And this manifold is the word that we talk about, starts here. but that is not the case. Let me rephrase that. That the 2p overlap is significantly, the head-to-head overlap in the 2p orbitals is significantly more than it is the side-to-side overlap in the 2px and 2py orbitals, which is why this is a lower energy than these. Except in some cases that's not true. And so what's the difference here? The reason why the difference here, and this is pretty complicated, and we make juniors and seniors think about this, is that there's some interaction between the 2s state and the 2pz state. And depending on which element it is, that interaction can be enough to flip the ordering of these two states. So be aware of which one is which. O2F2 is this one, everything else is this one, where the pi states are actually lower in energy than the sigma 2p states. Again, this is because the interaction between the 2s and the 2pz can make this go one way or the other. So just kind of remember which one is which. All right. The other thing to note is, in this case, I have drawn the orbitals that are made from the 1s. Now, as soon as you get to the second row, the 1s electrons are drawn in pretty close. They really have no interaction with their neighbors. This is the whole idea between valence electrons, right? And in the second row, the 1s electrons are not valence electrons, they're core electrons. So we tend, and if you look at these, if you actually do the math, what you find is that, number one, there's almost no difference in energy for these two. One of them happens to look exactly like a 1s orbital on one atom, and the other one is a 1s orbital on the other atom, and there's almost no physical overlap between the two states. And because of that, that's pretty uninteresting, it's cumbersome, it doesn't need to be there, so we tend to kind of ignore all but the molecular states built from the valence electron states.